The Hypnogram Report by Calvin Finney and Michael Rue.
Hypnograms show which stage a patient is in and how long they stay in each stage of the sleep cycle. They measure signals from the brain, eyes, and skeletal muscles in increments of 30-second epochs to get an accurate reading. Hypnograms may differ from each individual, but hypnograms from healthy patients follow a similar pattern. Sleep cycles have two main stages, REM and NREM. REM, or rapid eye movement, is known as the dream stage, and where majority of the brain activity during sleep occurs. NREM is the other part of sleep cycle, and the body activity varies. The body has specific signals that occur during REM, and that is how our device will determine whether or not REM is achieved. Our device will take in inputs from three different devices. EEGs are devices that measure brain activity and frequency of the signals. During REM, mid-frequency low amplitude waves are present. No K-complexes or sleep spindles are present during REM. EOGs are devices that measure eye movement, but also take into account brain activity. During REM, high amounts of eye movement are present. EMGs are devices that measure muscle movement. During REM, very little amounts of muscle movement are present. With these three devices and parameters for REM, our device will aid in identifying REM.
Since the signals from each of the physiological responses are all electrical, we need an electrical device in order to interpret them. This is why we obtain the signal from the EEG, EOG, and EMG. But that is not enough for the hypnogram to be able to interpret what sleep stage the patient is in. So, in order to do this, we must look at the various characteristics that are present within each of those signals. For the EEG, we have to determine whether or not we are within a low amplitude multiple frequency signal. And we also have to avoid both the K spikes and sleep spindles within the signal as well. In order to do this, we have to look at the frequency that is being given off from the signal, and then also the amplitude from the signal as well. For the EOG, we have to be able to determine whether or not eye movement is present over time. To do this, we have to just look and see if there are amplitude spikes that are present within the signal of the EOG. For the EMG, we have to be able to determine that there is no movement that is present within the muscles in the neck around the mandible. This again makes sure that there is no spikes within the amplitude of the signal. In order to determine whether or not we are within REM sleep, we must determine that there are no K spindles present within the 30-second epoch. So, in order to do this, we must cut off the amplitude at a certain point and then extrapolate that amplitude to the point of saturation so that we can have a signal that is viable to be interpreted with the black box. In order to have a cutoff for the amplitude, we must shift the signal down by a point at which the amplitude of a K spindle is going to be above. Now, K spindles are always at least greater than 100 microvolts. So, to do this, to isolate the K complex, we shift our signal down by 90 microvolts, and then if anything is above that, we have a gain that is so high that the op amp is then saturated, and then if there is a K spindle, a signal will be sent to the black box and then recorded. Within REM sleep, there are signals that are called low amplitude variable frequency signals. Now, in order to isolate these signals, we must first surround them by their frequency, which is 4 Hz to 7 Hz, and then we must amplify them to the point in which there is a viable signal that is given to the black box. First, to isolate the signal around that frequency, we have a bandpass filter. This bandpass filter, of course, goes from 4 to 7 degrees. To cut it off past 7 degrees, we have a low-pass filter that reaches 7 degrees at that point. This is seen within the first portion of this circuit right here with the 22.7 kilo ohm resistor and the 1 microfarad capacitor. With this, we establish a low-pass filter that cuts it off past 7 Hz. Then, to cut off the filter after 4 Hz, we have a high-pass filter. And this high-pass filter, of course, operates in the same way, and it has the capacitor of 39.8 kiloohms and 1 microfarad. Now, in order to determine the cutoff frequency for both of these, you have to do 1 over 2 pi, the resistor times the capacitor. And with these values, you will obtain the cutoff frequency for both the low-pass filter and the high-pass filter. In order to amplify the signal past that point, we have a op-amp that is saturated at 1 volt and has a gain that is significantly higher than any of the amplitude that is going to be present within the low amplitude variable frequency signal. And at that point, it will amplify it to the point to where it saturates the op-amp and then becomes present within the black box. There are no sleep spindles present within REM sleep. So in order to determine if these are present within the signal, we must first isolate around the frequency that they are present, which is from 11 Hz to 16 Hz. And then if they are present, we must amplify the signal to the point where it becomes a variable result for the black box. To do this, we create a second order bandpass filter, which effectively puts together a low pass filter and a high pass filter, and then allows the signal that is between them to pass through. The first section of this circuit is for the low-pass filter, which is going to cut off anything that is past 16 Hz. This is achieved by putting the resistor of 9.95 kiloohms and the capacitor of 1 microfarad together in a way that outputs a signal that attenuates it past that. Following this is the high-pass filter, which cuts off or attenuates any signal that is present before 11 Hz. And this is done by putting a capacitor and the resistor in series, and then with this 1 microfarad capacitor and the 14.47 kiloohm resistor, we achieve a signal that is attenuated if anything exists before 11 Hz. Now, if any sleep spindles pass through both of these filters, it will then be amplified to the point of saturation with this op-amp. This occurs with a high gain of about 1 times 10 to the 6, which will then cause any signal that passes through to exceed the saturation point and then give a 1 volt signal if a sleep spindle is present.
This part of the circuit will interpret data from the EOG signal. The voltage input represents the signal received from the EOG device. There is a DC offset present to ensure that the majority of the data will be negative. Positive data will be present if there is sufficient eye movement present during the REM sleep, or if there are K complexes present. During REM sleep, sufficient eye movement should be present, but there should be no K complexes present. So, in order to interpret this part of the data, the interpreter must reference the first circuit that measured K complexes. This circuit contains a large gain, but since the op-amp is saturated at 1 volt, the positive data will be maxed out at 1 volt, and the negative data will be set to 0. This part of the circuit will interpret data from the EMG signal. The voltage input represents the signal received from the EMG device. There is a DC offset present to ensure that the majority of data will be negative. However, this DC offset is lower than the previous DC offset of the K-spindle circuits because the muscle movements will be less than K-spindle peaks. Positive data will only be present if there is sufficient muscle movement present. During REM sleep, there should not be lots of muscle movement because the body releases paralyzing chemicals to inhibit muscle movement during REM. This circuit contains a large gain, but since the op-amp is saturated at 1 volt, the positive data will be maxed out at 1 and the negative data will be set to 0. Each circuit will output a digital signal with either 0 volts or 1 volt. Each circuit has certain parameters that need to be met for a voltage output of 1 volt, as previously discussed. Depending on the circuit, 0 volts or 1 volt are preferable for REM state. The outputs for each circuit should be 0 volts, 1 volt, 0 volt, 1 volt, and 0 volts respectively for REM state. If any of these vary from the expected values or if they change during the 30-second epoch, REM state is not achieved and the interpreter should realize that it is NREM for that specific 30-second epoch.